Greetings everyone. So the topic of this video is going to be the histogram analysis that is used very frequently in chaos-based image encryption. So first of all, let's talk about image encryption in general. In chaos-based image encryption, the idea behind it is during the transmission that you use some sort of chaotic source, like a chaotic system, for example, in order to encrypt some information. And then this information becomes scrambled and incomprehensible, so you can safely transmit it to a public channel. And then at the receiver end, during the decryption, you practically reverse this project using this process, using the same chaotic source. Okay, and of course, to do that, you have to know the secret key that is used during the encryption. So, of course, this is a much general process. There are many different techniques in the literature on how to do that. And on this video, we are not going to discuss about the different techniques. We are going to discuss specifically about the analysis that is performed after the encryption. Okay, and specifically the analysis through the histogram. Okay. So first of all, let me point everyone to the very well-known CP database. This has a lot of images that are very commonly used in encryption and chaos-based encryption papers. So you can visit this website and download any images that you want in order to use in your own works. So I'm going to discuss two very simplistic processes that are commonly used in chaos-based encryption. The first process is the process of permutation, okay, most commonly known as shuffling. So what do we do in this process? In this process, what we do is take an image and through some sort of chaotic source, define some rule in order to shuffle the pixels of the image. Okay, much like you see in the second picture, like here. The whole idea is the same as shuffling a deck of cards, right? The idea is to disperse information throughout the image in order to obtain something like that makes no sense when you look at it visually, but as we will see, still carries some information. The idea is to disperse various parts of the image throughout the whole shuffled image. So in case, for example, some sort of cropping occurs, we may be able to receive back some information. So this is the first process that is very commonly used in encryption. And the second process, which is actually the strongest one, is substitution. Substitution, which commonly happens through the exclusive OR operation, but there are other ways, of course, is the process in which you take a specific pixel value, as you see right here, and you replace it with another value. And this completely hides the information behind the image. So the final encrypted image is the image that results after these two processes occurred. Okay. In another video, we may also discuss different methods to achieve this. Okay. So after we perform this encryption, the idea is to take the encrypted image and study its histogram. And the reason we do that is because the histogram practically reveals a lot of information about the way that the pixel shades are, distributed in the image. As you can understand, naturally, if I take a photograph myself and I take the histogram of the pixels of this image, naturally, the histogram will be non-uniform. Obviously, because there are certain shades of gray that appear more often than others. And you can see it here in the Peppers, the very well-known Peppers image. The original histogram is non-uniform, obviously. And then if we take a look at the shuffled image, you will see again that the histogram happens to be non-uniform. This, of course, may come as a surprise initially, but if we think about it, it makes absolute sense because think about a deck of cards, like it has 4 cards of kings, 4 cards of queens, 4 cards of aces, and so on. Well, if I take this deck that I just bought and I shuffle it, how many kings do we have? We still have 4 kings. How many queens? We still have 4 queens. How many aces? We still have 4 aces. So the idea is this, regardless of the fact that I have shuffled the pixels on the image, so visually the image now makes no sense to me the way that if I look at it, I don't understand that it represents the Peppers image. Still, if I take a look at the histogram of this shuffled image, much like a shuffled deck of cards, is the same as the original image. So the histogram distribution in this case is exactly the same as in the original image. So this is why you see, regardless of the fact that the shuffling scrambled the image to our naked eye, it still is not secure enough. Okay, and this is why we need the secondary step, the substitution step where we replace every pixel value with something else. And that's why you see that in the purely encrypted image, the histogram now is purely uniform, which means that it practically reveals no information at all about the image that it actually represents. Okay, and that's the result of the actual good encryption, that it can manage to completely obscure information about the distribution hiding behind the pixel values in the original image. Okay, you can check the variance as well. It's significantly lower in the encrypted image because obviously you have a much more uniform distribution of the pixel values. And this is why we need both steps in encryption. You see, the first step of shuffling is not secure enough. We need to have the substitution step in order to be secure against statistical analysis through histogram. Okay, this is why most works check the histogram. Okay, and of course I showed this to you for gray image, but the same idea is behind color image encryption. Okay, see here the color version of the papers. We have three channels, so basically we have three matrices: red, green, and blue. And usually the encryption in these cases follows some sort of combined encryption through all the three channels simultaneously. And you see on the bottom the encrypted versions of the red, green, blue channel, as well as the original combined channels, right? And the approach through histogram analysis again is the same. The only difference is that in color images we study the histogram of all three channels. Okay. So in the original image, the histogram in all three channels was non-uniform, but in the encrypted images that I'm showing on the bottom, all three channels of the encrypted image are uniform. So this means that regarding histogram analysis, our encryption is secure. So by taking a look at the histogram of the encrypted image, some adversary cannot reveal any information about the hiding, the hidden image behind this. Okay. So this is the whole point of having histogram analysis in encryption, specifically chaos-based encryption papers. Thank you very much, and we're going to have a future series of videos where we explain different statistical measures used in analyzing chaos-based encryption.